you for the invitation, Chris and Sophia. I think I got the invitation for the fall, and then some things happened. So I'm happy to be here and to be able to give you this presentation. So I've been working on what in econometrics we call difference in differences methods. And, you know, I'm getting at this stage in my career where I don't, you know, release things that I feel comfortable with, you know, very easily. And so partly I started thinking about ways to simplify some of the research and difference in differences, partly for teaching purposes and partly to make sure people who actually are doing policy analysis, intervention analysis, have kind of a broad enough set of tools and understandings about these methods. So I wasn't quite sure what to do here in terms of the slides are maybe a bit dense and maybe technical for an overview talk, but I really want to emphasize that clearly all of you are have the tools to follow how the difference in differences literature has progressed recently in the econometrics literature, and certainly there are crossovers here with various fields, including statistics and biostatistics and public health and so on. So, and there was this recent paper in the American Economic Review Paper and Proceedings by Curry, Clevin, and Zwires on, you know, what sorts of methods are popular in empirical economics, and difference in differences has seen a huge upsurge in the last 5 to 10 years. And this led to a re-examination of the most common ways that people were implementing the method. Now, there's some confusion, and I'm going to point this out later, about what we actually mean by difference in differences. The name comes from a very basic setup, which I'm going to go over the starting point because I think it provides a bridge to the more complicated settings. And you can see that as people who are familiar with causal inference and potential outcomes, that this really is all quite familiar in terms of how it's being set up. So the idea, of course, is that if we have at least 2 time periods where we have a time period, you know, where we observe outcomes on units prior to an intervention, and then an intervention occurs, and then we see the outcome, that allows us to do some things in economics. We think of it as controlling for unobserved heterogeneity, which are factors about individuals or firms or counties or whatever that don't change over time. And then, of course, in many cases, we want to explicitly control for what I'll call observed heterogeneity, which of course we can call covariates or conditioning variables or whatever your favorite name is there. Now, difference in differences methods can apply to pooled cross sections or panel data. I'm going to focus on the panel or longitudinal data case because that's the easiest one both to talk about and the notation is easiest. Actually, I've been known to claim in the past when I've talked about the pooled cross-sectional case, in the simplest case, this is what statisticians would call analysis of variance, except that we're not interested in really the components of the variance, you know, breaking that down. We're interested in estimating what we would call a contrast, which is, you know, a linear combination of averages across different groups. The panel data case, like I said, most of the recent research in econometrics has focused on that case, not all of it. So in this name difference in differences, I have to say I don't particularly like it because it has led to lots of confusion, I think, among researchers who actually try to take a more complicated setting where they may have an intervention which is rolling out at different time periods. And so there may be a change in, you know, a minimum wage, for example, and let's say it's at the county level, or there's a change in certain ways that police departments use, you know, things like body cameras you know, as a regular tool in criminal justice. And these things don't all happen at the same time for all of the same units. And so that's called the staggered intervention case. And the name difference in differences has this connotation, and I'll review for you where it comes from, that makes it difficult for people to kind of say, well, how do I fit this more complicated case into this simple setting, which, you know, I've learned in really my introductory econometrics classes. And so a lot of focus is on basically this estimation approach, which, or this modeling / estimation approach, where basically people tried to take the simple 2-period case where you have this before after and look at cases where you might have multiple periods prior to the intervention. It may be rolled out at different times, and then, but you're estimating an equation, a model that has a single treatment effect. And so a lot of the attention was initially focused on, well, what if you impose this single treatment effect, but in fact, there's lots of heterogeneity, both across time, as well as what I'll call cohort, where a cohort is going to be that, you know, some units are treated in the first period, some more units are first treated or subjected to the intervention in the second period, and so on. And of course, all of these units and time periods could be different from one another. And that was the focus of this pretty recent work by these sets of authors. They were working on this problem independently. These have now both been published in journals. And I should say the references here, sorry I didn't fill them in a little better. They can all be found in this working paper of mine, and I can make a link available to anybody who's interested in that, and a bunch of Stata code and so on that implements these methods. Okay, with a talk like this, I'm kind of leaving out the practical implementation just to try to show you where I think the literature is and where it might be going. Okay, so so the idea is, what I show in my recent research is that it's not, you know, to blame this on an estimator, which we call the two-way fixed effects estimator, is really incorrect. And the real problem is that the estimator is being applied to a model which is too restrictive. And so, as I often emphasize to my students and to others who might listen, is I really want to separate the modeling problem from the estimation problem. And that sounds so obvious, but my reading of this literature is that these two things are being conflated, and it's important to actually keep them separate. Okay, so so I'm going to get to that at the very end once I set up kind of the basic problem, and then show you why it is we need to deviate from the simple case where the estimator has a simple form. Some more recent research on this is due to Callaway and Santana, and what they do is they use an approach which has come to be known as long differences, where you look at outcomes after the intervention and you compare them with outcomes before the intervention. This clearly has a difference in differences flavor, but as it turns out that you're throwing away information by doing that, because if you have any kind of multiple pre-treatment periods, then you should be averaging that information, not just using the outcomes at one point in time prior to the intervention. So, I'll mention this briefly again. I'm going to show you how you can kind of get to what they're proposing in the simple case, and then talk about some very recent research I'm doing with a current student of mine in more complicated cases. So there is this assumption that you tend to hear about a lot in these sorts of settings, and it's known as the parallel trends assumption, or actually I'll call it the common trends assumption as well. And this has to do with what are the differences between the treatment and the control group in terms of what the trend would be in the absence of the intervention. And so the idea is there essentially self-selection into the intervention or the treatment based on different ways that the two groups are trending? And I'll formalize this assumption shortly so that you can see exactly what it is in terms of potential outcomes. adding control variables can help make this parallel trends assumption true. And that's where the real emphasis has been in trying to, mimic, in a sense, what we do in a cross-sectional context when we want to do a treatment effects analysis and extend that to the panel data case with multiple time periods. Okay, so I want to start with the common timing case. And in fact, I want to start with the simplest version of the difference in differences setting, which is where we have two time periods. So the first time period, no units are subject to the intervention. And then by the second time period, some intervention has occurred, and then we measure the outcome. Okay, so this is so the treated group is going to be those units that are subjected to the intervention. And so in this case, we can define a single dummy variable, and this just indicates whether the unit is eventually treated or not. None of the units are treated in time period 1, so that acts as a control period for both groups. So in the spirit of, kind of potential outcomes, we can think of there being four potential outcomes. These are the ones that are most natural because there's an intervention, and we can imagine every unit I in both states of the world. This is where they didn't receive the intervention or treatment, and this is where they did receive it. Okay, and then we have to be careful a little bit, because once we know that some units are going to be treated and not treated, we really do have to talk about what the potential outcomes are in the period prior to the intervention. Now, this becomes a bit dicey, actually, and we pretty much just have to assume something about what those potential outcomes are, because since there are no units treated in the first period, we don't have any way of estimating a treatment effect in the first period. So one version, and this is the one I'm going to impose for the purposes of this talk, and there are ways to relax this a bit, is called a no anticipation assumption, which simply says that there are no treatment effects in the initial time period, so that people aren't changing their behavior based on what they expect their treatment assignment to be. And this, of course, can be violated if people know that some sort of policy is coming, or some sort of like a job training program, or some sort of voucher program for attending schools, and they change, their behavior prior to that. So it's not an assumption that's for free, but it is an assumption. This is implicit in a lot of work, actually, in the econometrics literature, and only recently, relatively recently, have people pointed out that this is actually an assumption. Okay, so for the sake of argument, I'm going to assume random sampling in the cross-section. You can turn this into a finite population analysis if you want to, but I want to focus on the so-called identification issue rather than issues of, how we're actually doing the sampling. So let's think of, and this is random sampling in the cross-section, right? So we have a random sample of individuals or firms or schools or something like that, or classrooms, whatever we're looking at, or hospitals or whatever. Okay, so the parameter that's typically the focus in these studies, in this simple setup, is the so-called average treatment effect on the treated, and this is necessarily in the second time period, okay, where we actually have some treated units and some control units. And so this is defined to be the average gain, if you will, gain in quotes, because of course it could be a loss for some and a gain for others, for the group that actually receives the intervention. Okay, so this is the usual, problem in, missing data problem in the context of potential outcomes is we have no problem with this first term because we're going to observe this for the treated units. But the problem is here in that for any unit that is in the treated group, we don't observe what their outcome would have been in the other state. Okay, so I know this is kind of stating the obvious for this group, but it's just a reminder that this is, where this, where the problem of causal inference comes from in this particular setting. So the data that we have in this simple case is we know their treatment status, and we know what the outcomes are in the first two period, in the first period and the second period. We're going to assume that we observe the outcome and it's the same outcome in both the eventually treated and control states. And then we can write the observed outcome Y2 as this, in this simple way where this simply picks off the potential outcome based on the treatment status. Okay, now just to remind you, so I want to, just remind you why having the two time periods is such a powerful thing. And that's because if we suppose we didn't have the initial time period, so we only observed the outcome in time period 2, well, and we don't have any covariates or control variables, so what we would be stuck with is using the basic difference in means estimator, right, that we learn and teach in basic statistics. So that estimator is to simply average the outcome in the second period for the treated units and subtract off the outcome for the treated units, and subtract the average for the control units, okay, where these, of course, are the number of treated and control units respectively. Okay, so this estimator, of course, if we had a randomized control trial in the second period, then this estimator works just fine in terms of giving us unbiased and consistent estimators. But in general, if there is some sort of systematic, violation of random assignment, then we can write the probability limit of the simple difference in means estimator in this very simple way. And one way that economists think about this is what we would like to have, the average treatment effect on the treated, but in general, there's this selection bias term. And this selection bias is the difference in the means in the control state based on treatment status. And so if there's some sort of systematic self-selection into the program, let's say, or somebody knows more than we do, and they're putting certain kinds of people or schools or classrooms in the program, then this is going to systematically bias this estimator is going to have systematic bias. So the question then is, how can we exploit this T=2 panel structure? And the answer is we use the so-called difference in differences estimator. And so instead of looking at the difference in means in the second time period, in the panel data case, we look at the change in the Y from period 1 to 2 down here, and we average that for the treated units, and then we subtract off the change in the Y for the control units. Okay, and so you can see where the name difference in differences comes from, because we're differencing over time. That's the first difference. And then we're creating the difference in the averages over the changes, and that's the second differencing. And so hence the name difference in differences. Okay, and because we have panel data, we can difference each unit by itself, okay, from period 1 to 2. So we have the change in somebody's earnings from before the job training program to after the job training program. Okay, so now a question is, and I don't want to get too bogged down because I tend to get bogged down, is when does this difference in differences estimator consistently estimate this treatment parameter that we're interested in? Well, under no anticipation, we can write the parameter that we're interested in like this, okay, because we don't have to worry about this, this difference in the outcomes in the first period. So I'm skipping over the algebra here. I have a longer set of slides. If anybody is interested in those, I'm happy to share those, but the algebra is actually pretty easy. So the idea is this part is always estimable, because, as I said, this is for the change in the potential outcome in the treated state, and we're conditioning on the treated subpopulation. And so the thing we observe for this subgroup is exactly what we need to observe. So this term is always easy, because all we have to do is average the change in the outcome for the treated group, and this is going to converge in probability to this mean that we need. Okay, clearly this is basic statistics, right? But the difficult term is this one, because this means we have to figure out what the average change would have been in the control state for those units that were subjected to the intervention. Okay, and this is where the so-called common or parallel trends assumption comes into play. Well, if we need to estimate this, then why don't we just assume it's the same thing as the quantity that we can estimate it? In other words, the average trend or the average change in the over time in the untreated state is the same for the treated units as it is for the control units. Now, this is better than assuming that the levels in the second period are the same, because this allows, in particular, this allows the treatment assignment to be correlated with the outcome in the first period. Okay, so it's allowing for certain violations of random assignment. Moreover, it actually allows the treatment assignment to be correlated with what one might think the change in the outcome would be in the treated state. Okay, but this is really, I think, the most important one, because this allows clear violations from random assignment, but it does impose this restriction. Okay, so this is like essentially random assignment, but it's with respect to the trends, not with respect to the levels. Okay, and so under these assumptions, I didn't write it out formally. I showed you what the no anticipation assumption was. And the common trends or the parallel trends assumption, the difference in differences estimator does consistently estimate the average treatment effect on the treated. Okay. Okay. So then I left this material and I want to get through this quickly because this is mechanical stuff. But the reason I left this in is because in my recent work in more complicated cases, it was starting with this simple case that made me start to think that maybe there, these different estimators that people are proposing, that there were commonalities that weren't fully being appreciated. And so it's easiest to explain them in this very simple case, and then I can apply the hand wave operator and you'll hopefully believe me in more complicated cases. Well, I'm actually going to apply it here because obviously I'm not going to prove any of these assertions, but some of these are quite easy to see. Okay, so we can, the difference in differences estimate can be obtained as a cross-sectional regression where we simply regress the change in the outcome on a constant and then the treatment indicator. This is, again, kind of the simplest problem in regression that you can have. The coefficient is the difference in differences estimate is the coefficient on D. We know how to do inference on this. By the way, and we can contrast this to the simple difference in means where we regress the level in the second period on a constant and the treatment indicator. So you can see we're using the change here and we're using the level here, and it isn't any deeper than that. Okay, so a second one, which is not as clear, is that we can actually set this up as a pooled OLS regression where instead of differencing, we actually just use the n times 2 observations. This is the cross section. This is the number of time periods. And to do this, we define a dummy variable, which simply indicates whether an observation is from the first or the second time period. Then we can actually define a time varying treatment indicator, which is this interaction term, which you see so much in the difference in differences setting. So it's the interaction between eventually being in the treatment group, which doesn't change over time, and the time dummy, which does change over time. And actually, I would strongly recommend having this variable defined, because when you get to more complicated settings, including some nonlinear models, it's really helpful to have this. Okay, so this is the variable that I like to have in my data set, regardless, of the fact that I can reconstruct it using those two variables. So I just wanted to emphasize, you know, what a data set would look like in this case. This is a job training data set from the early 1990s. This is my time dummy. This is the D variable that's either both 1 in both periods or 0 in both periods. This always has this pattern. And then this is the time varying treatment indicator. This is my W here. Okay, so this is just to make sure you understand what the distinction is among these three variables. Okay, so what you can show, and this follows as a special case of the results in my recent working paper, is that if you do a pooled OLS regression and you control for whether you're ever treated, you control for time periods so that this is accounting for secular changes over time, and then you put in the treatment dummy, you can show that you get exactly the same estimate as the previous regression. Okay, and so this kind of paves the way to thinking about what happens in more complicated situations. And of course, it's the same thing as to do this kind of standard regression that you see a lot, where the treatment variable is this interaction term. Okay, but in more complicated situations, you can't define this interaction term as being the single treatment variable. And so I don't want to put too much on this right now. Okay, here's a third way of getting exactly the same estimator. And this one is kind of interesting because it shows that controlling for lots of heterogeneity in this setting turns out to be unnecessary. And what I mean by lots of heterogeneity, I mean we're going to put in literally a dummy variable for every cross-sectional unit. So if we have 1,000 counties or 3,000 counties that we're doing some sort of before after policy analysis, we put in a dummy variable for each of those 3,000 counties. We put in a dummy variable indicating time. Then we just have the one variable, the treatment variable, and it turns out that this is also the same thing as tau 2 hat. Okay. So this is the same estimator, and I forgot to emphasize that it's the same estimator. I guess I should be a little more careful. This is the difference in differences estimator. So this is a third way, and it's interesting because what this shows is it's actually enough to control for just this single dummy variable, indicating treatment versus non-treatment, and that gives you the same as controlling for all of these dummy variables. It's numerically the same estimator. Okay, so there are actually more estimators that are equivalent to this. It turns out there's a random effects estimator for those of you who kind of use that terminology like econometricians do, and that's also equivalent to this, but I won't get into that. Okay, so now what is the role of covariates in these sort of difference in differences? Well, I'm going to focus on the case which has received the most attention lately. There's some movement away from this, but this is the case where we have covariates, control variables that are determined prior to the intervention. So in other words, these are good controls in that they can't be affected by the intervention because they're already determined prior to the intervention. So this is what we do. We kind of emphasize this when we do treatment effect stuff, right? Is we don't want to over control, although there is such a thing I know as mediation analysis and so on, but I'm not going to get into that here. These are pre-intervention covariates, and so they don't change over time. They're collected prior to the intervention, and then we have them. Okay, now how can we use them? Well, here's what we want to do. We want to relax the parallel trends assumption. So this is exactly the same formula that I had before, and this first term is still not a problem. This second term is still the problem. But what we want to do is relax this assumption that says just when we take the average of the trend in the control state for the treatment and the control, that these things are the same, because this seems still like it could be a fairly strong assumption. So what we want to do is relax this by effectively partitioning the population into subpopulations based on these values of the covariates. So Others and I have called this the conditional common trends or conditional parallel trends assumption, because now this basically says, once I control for these X's, then the treatment status, then the trend does not depend on average on the treatment status. Okay, so this is an unconfoundedness or ignorability assumption, to use the language from the treatment effects literature. It says that conditional on X, the treatment is unconfounded with respect to the change, this potential outcome, because we don't observe this for the treated group. And this is all we need to estimate the average treatment effect on the treated. Now, if we go back to the cross-sectional case, what we would be doing is saying that D is unconfounded with respect to the level of the outcome conditional on X. So the hope is that by focusing on the differencing and by being able to control for the X's, we can make this common trends assumption true. Okay, now, again, sorry for the busyness of these slides, but I really want you to see that all of this is really pretty easy for all of you who are trained in causal methods. I mean, all you have to do is basically make the connection that we're using unconfoundedness here, but it's unconfoundedness in the change or the difference rather than the level. And so the key step is going from conditioning on the treated subpopulation to conditioning on the control subpopulation. The first of these is the law of iterated expectations. The second of these is the conditional common trends assumption. But see, now this thing within the braces here, I can estimate this because this is now, I observe this change for the control units, and I have to condition on the X's, but that's, we know how to do this via regression analysis. Okay, so this conditional mean function is estimable using the control group because we observe this change exactly when we have to now. So we've relaxed this common trends assumption to this conditional common trends assumption, and now this allows us to do regression type adjustments. Now, as you know, when you do some sort of regression analysis or propensity score weighting or matching analysis, this what we call, at least in econometrics, we call it this overlap assumption. And this simply means that we need the probability of treatment to be strictly positive, for all X's in the support of the distribution. Okay, so this is the standard assumption. Actually, you know what? I actually think I have this wrong here. I think this is supposed to say less than 1, actually. Okay, this is this means that there can't be any subsegments of the population where the probability of treatment is certain, okay, because we need to be able to get a control unit in the other treated state. Okay, so what this means is now we can estimate the second part. This is the second part of this average treatment effect on the treated. And we're going to be able to estimate it because this function is identified. And then assuming that we have overlap, we can average this function. We can do the extrapolation to the treated units. And then this is just going to be estimated by a simple averaging over the treated units. Okay, so now we have this data set, right? We have the data set on the change in the Y, the treatment status, and the X's. Okay, now regression adjustment is clearly the first thing, at least that I would think of using here. And so I'm going to, since I'm running out of time, I'm going to jump to the way I prefer to think about this. But what we're going to do is use the control units to do a regression adjustment where we regress on the X's. And then we do this kind of imputation of this conditional mean. Of this unconditional mean, or it's conditional on D equals 1. This is the one we can always do, and this is the one where we have to impute based on regression analysis So we've used the parameters estimated from the control units, but we're now averaging over the treated units. Okay, and in order for this to be convincing, we have to have this overlap assumption so that we've estimated, the same sorts of x's that were used to estimate alpha 0 hat and beta 0 hat are available in the treated subsample. Okay, now there's this other way of thinking about it. And again, this is an algebraic equivalence that isn't too difficult to show. I show a more general version of this in my paper. And it's to include an interaction term. So we take the change, we regress on a constant, we put in the treatment status, we control for the x's, and then in fact, it's important in some cases to put in the interaction. And to make sure we get the average treatment effect on the treated, we center the x's around x1 bar, and I should have said this is the average over the treated subsample. Okay. One thing I like about this representation is we're actually interested in these coefficients sometimes because these give us the so-called moderating effects, right? We can see whether the treatment on average is different across different subpopulations based on the x's. Okay, so I like that. It's the same as running two separate regressions. I'll skip over that. This is just an algebraic equivalence. And also it's the same as an even longer pooled OLS regression where you have to put in every interaction term that you can think of. So this is the treatment indicator. This is the interaction of the treatment indicator with the x's. So it's these coefficients now when we pool across the two time periods that contain all of the treatment effects. This becomes a control, as does time, as do the x's, and then we interact. We put in, like I said, as many interactions as we can. Again, in my paper, I show that these things are all equivalent. And that means that when we get to more complicated settings, this kind of pooled regression is going to be quite handy. Okay, and I know I'm going to, push this, so I want to move this along. Moreover, there's a fixed effects version of this estimator as well. And because we're putting in the fixed effects here and the time effects there, these are the cross-sectional fixed effects, anything that doesn't change across time gets eliminated. And so we can drop this and this, those two things, and the x's by themselves. These all get dropped because they don't change over time, and we're doing this fixed effects estimation. Okay, I like to call this extended two-way fixed effects because but it's really the model that is being extended. The estimator works exactly the same, but I'm allowing for the treatment effects to change with x, and I'm allowing for the effect of the x's to change across time as well. In my view, this is as flexible as one can be in this two-period setting. Other than doing non-parametric regression, I really don't know what one would do here. You either do it this way or you do it this way with this full set of interactions, and they are numerically equivalent. Okay, and you can, if you go to my shared Dropbox, which I'll share with you at some point for anybody who's interested, I have a bunch of stata demonstrations that show how all these estimators are in fact exactly the same. Okay, and that follows from my work there. Okay, so I do want to at least make sure that, so one of the things that then comes out of this is once we understand that in this simple case, this is just regression adjustment where the dependent variable is the change over time from period 1 to 2. Now this opens up the door to any kind of estimator that we want. And I should have given Alberto Abadi credit for this. He suggested propensity score weighting in a paper that was in the Review of Economics and Statistics many years ago. But in current work with my student, where we're extending this to the multiple period case, we make the following very simple point. This student's name is Sujiang Li. She's a third-year student currently at MSU. Is you can apply anything that you want. So if you like to use propensity score weighting, you can do that. Here's your data set. we're going to estimate a propensity score model for the treatment. If you like to use some sort of matching, whether it's on the covariates or propensity score, you can do that too. I actually like these doubly robust estimators as a way of modeling the mean function for the change in Y, as well as the propensity score, and then getting this doubly robust property out of having to only correctly specify one of them. But the point is, you can do this, and for those of you who are familiar with Stata, this t-effects command in Stata does all of this stuff. And the only thing is you apply it to the change in Y rather than the level of Y itself. Okay, so I don't have too much time to get to the frontiers, but I want to just comment on something here. So in my working paper, the first thing I did then is I said, well, what if we have multiple periods before and after the intervention? That means we have multiple treatment effects, because we can have a separate treatment effect for each of the treated periods. This means now the treatment started in period Q, so Q is the earliest period, and then we can go all the way to the end. Well, what I show under basically the same assumptions, the no anticipation and the common trends assumption, they have to be modified a little bit, but not in any important way. You can write down this equation, which is an extension of the model with interactions that I showed you previously. So the X's have been demeaned from the average in the treated subpopulation. And if you look at this, you'll see that we're controlling for D, we're controlling for the X's, we're controlling for the time effects, we're controlling for interactions with everything. And then when we get down here, these are the coefficients that we're interested in. These are the average treatment effects on the treated. And then these are the coefficients that allow us to do some moderating analysis to see whether the treatment effect changes not just across time, but also across covariate values. And so we know how to estimate an equation like this, right? This we can estimate using OLS, pooling across both cross-section and time period. And so that's what we do. And so this is the regression, and it's getting to be a long regression, right? But this is incredibly trivial compared to machine learning and all sorts of things we do these days, right? This is just putting in, these are all control. So sorry, I moved this to the beginning. These are all the treatment variables. And then these are all acting as control variables. And because of this centering, we force the coefficients on these variables to be the treatment effects that we actually want, okay? And also, there's a two-way fixed effects version of this, where when we apply two-way fixed effects, all of these things become irrelevant because they don't change over time. We still include the time effects and all of the interactions of time dummies with the X's, okay? And they're numerically equivalent, okay? So that is, has been shown in my paper. Now, what I'm doing with also with my student Su Jiang is we're extending what the differencing approach in the two-period case to this general case, and I'm really kind of enthusiastic about this work, because what we've shown is that you can reproduce these estimates here. This is getting messy. We can reproduce the coefficients tau hat sub r, where r is running from period Q up to t, by actually transforming the data where we take the outcome on Y in a post-treatment period. So it could be Q, Q plus 1, all the way up to T. And instead of differencing, we subtract off the average of the outcome prior to the intervention. And you can show that applying regression adjustment to this modified variable is exactly the same thing as this pooled OLS regression, which is the same thing as two-way fixed effects. Why is that convenient? Because now we can take any of our favorite treatment effects estimators that I just talked about, and we can apply them to this transformed data set. And now we can get something like, I'm especially fond of this version of the doubly robust estimator because I essentially proposed this in a Journal of Econometrics paper in, I think it was 2007. So this gives us a way to estimate these effects that are changing over time, okay, in a doubly robust way by combining regression and propensity score stuff. Okay, I'm actually close to finishing, and so I just want to mention the most general case. Now, this one is interesting because in this one, I admit we're working on this, but we haven't quite found the magic transformation in the staggered case that reproduces the pooled OLS / fixed effects estimates. Now, I would like to do that, but actually I feel pretty good about this kind of regression framework because the simulations I've done show that it works quite well, and it's actually hard to beat. I mean, my view is always it's really hard to beat a well thought out regression analysis, right? I mean, we know that it doesn't always work, but if the idea is to just kind of throw out information that's in the data set, you're going to be hard pressed to do that and to systematically beat ordinary least squares. Okay, so the staggered intervention case, the way I set up this problem is I thought of there being different treatment levels now. And the treatment level is determined by the first period subjected to the intervention. And by the way, I've thought about the case where the intervention happens and it goes away, and I talk about this a little bit in the most recent version of my paper, but I'm thinking of cases where there's an intervention and then it stays in place until the end of the period. Okay, so there can be many periods before the first intervention. Maybe all of the units are eventually subjected to the intervention. That's in my paper. I'm not going to mention that here because that changes the notation. It's easy to allow simple violations of parallel trends, okay? And so the idea is now we have even more treatment effects because the treatment effects are indexed by two indices now. One is the cohort. When is the first period a unit was subjected to the intervention? And then after that, there can be treatment effects in every time period. So for a cohort G, we can see their treatment effects starting in G up until the end of the period. Okay. This is kind of a strange notation, but I borrowed it from a paper by ASA and Imbens because I was struggling with this idea of calling this Y0, because what we're really saying is we're comparing the outcome in the state of first being treated in period G with the outcome in the state of never being treated. Okay, so this is where this idea that there's a group that is never subjected to the intervention comes into play. Okay, so this is not really my definition. This has appeared in this recent work in the staggered intervention, but I think it's a nice way to kind of think about what we're comparing these cohort outcomes, these potential outcomes with, and we're comparing it to the case where a cohort has never been subjected to the intervention. Okay, there are no anticipation assumptions, of course. There are common trends assumptions, and this one especially is more complicated because now there are these different cohorts which are indexed by DQ is the first cohort treated up to DT, and this indicates the cohort treated only in the final time period. Okay, and so what I derived in my paper is this formula, which you can see is getting longer and longer, but this is just an equation which is linear in a bunch of parameters, and we control for all of the cohort dummies. We interact all the cohort dummies with the covariates. We control for all of the time periods. We interact all of the time period dummies with the covariates. And then these are the treatment effects down here. And you can see what's being done down here is with this triple difference is we're estimating this is the treatment indicator, and we can think of this as allowing for this full heterogeneity where the heterogeneity is defined by cohort and time period. And of course, we can only estimate a treatment effect for time periods after a cohort was subjected to the intervention. This final term allows for additional flexibility, and these are actually demeaned by cohort. Okay, so these, I should have written that definition. These are the demeaned X's by cohort, okay? And that forces these to be those average treatment effects that I had on the previous slide. And so again, we might be interested in these coefficients to do some sort of moderation analysis. Okay, and I see I have a couple of questions, but hopefully you'll bear with me. Okay, so this is just a long pooled OLS regression. I show that there's an equivalent two-way fixed effects estimator. And so now we can see the complaints about the two-way fixed effects that were the basis for a lot of this work come from the following. Instead of having all of these terms, all of these treatments and all of these indicator statuses, all of this is replaced with WIT, and we multiply it by a single tau. I'm not very good. This is the formula of the sum of the first, I mean, what is it? The sum of the first T minus Q integers or something is how many treatment effects there are here. So we can do better than two-way fixed effects by putting in all of this heterogeneity. And then we can also allow the effect to change with the X's. In addition, we're allowing full flexibility in the covariates as well. And so if we do two-way fixed effects, these terms are all going to disappear. But as I show in my paper, the estimates here and here are numerically identical. Okay, so it doesn't really matter how we do it. Now, as I point out in my paper, doing it via two-way fixed effects does have one advantage, and that is we know that this has some resiliency to the case where you have missing data, and so you have an unbalanced panel. Okay, so this does have some preference in the case of an unbalanced panel, but in a balanced panel, they're numerically the same. Okay, this estimator I also show in the paper is efficient under what we call a random effects structure. You might call an exchangeability structure. Okay, the leading competitor to this is this work by Callaway Santana, which came out in the Journal of Econometrics, and this is this long differences approach. Okay, and so I've done some simulations, and it's much less efficient because, you know, if you know the efficient estimator is this one, then you can't improve over that unless there's a violation of these assumptions. So it's less efficient for sure. It can be more resilient to violations of common trends. Okay, but I will point out that it's very easy to allow certain violations of common trends within this setting. You take this equation, which I've now mucked up, and you ask, what more can I add to this equation as a robustness check? And the answer is, I can allow each cohort to have its own linear trend. With a lot of time periods prior to the intervention, I can allow for more flexible trends. I could put in quadratics. And I might even allow them to have its own trend by X's as well. As long as we don't have a shortage of data, so I'm kind of assuming that we have a reasonably large cross-section, and that there are enough, treated units, new treated units in each cohort, then this is just incredibly easy to do. And like I said, I'll invite you to look at my shared Dropbox that I actually have shared on Twitter to study these things if this is something that interests you. Okay, so finally, this is the last slide. The even more recent developments is to extend this to so-called nonlinear difference in differences. And I'm supposed to give a talk on this soon coming up. I gave a preliminary version of it in the fall in a STATA conference. And I really think this is pretty neat, because you can take this pooled OLS analysis here. So you can take this equation, and basically all you have to do is replace this linear equation with a, what are you guys, I always forget the terminology. The inverse of the link, is that right? Anyway, I'm just going to tell you what I mean by that. Is I can apply a logistic function and everything goes through. You know, when I properly define the average treatment effects on the treated, or I could use an exponential mean function. This would be especially attractive for count variables and other variables. And because these are both members, the Bernoulli and the Poisson distribution, these are both members of the linear exponential family, and these are the canonical link functions, or they're associated with the canonical link functions, you get some nice algebraic equivalences, and you get this robustness to misspecifying the distribution. So the Bernoulli distribution can be arbitrarily wrong, and the Poisson distribution can also be arbitrarily wrong. I have the preliminary work on this also posted on my shared Dropbox that shows how this actually works, along with some slides for that talk. Okay, so I've probably gone a little too long, but I'm certainly happy to take the questions now. And I see that the Q&A here is okay. So yes, very good. So there's a question here about when the interest is for the entire population rather than just the treated, should the centering be around X bar? This is exactly right. And the reason why I didn't cover that case, well, for time, but what you have to do is you have to strengthen the parallel trends assumption. And what you have to do is state it in terms of the potential outcome in the treated state as well as in the control state. Okay, but one might argue that if we're willing to assume parallel trends in the control state, we might also be willing to assume it in the treated state. And then you're exactly right. The centering in that case would be xi minus x bar, where this is averaged over the entire sample, not just the treated units. Okay, possible to share the link. So I'll, yeah, actually, I don't know if you go to if you go to Twitter, you can find my account, and the link is the pinned tweet at the top. Okay, if not that I'm really not trying to get more Twitter followers, but that's where interest was shown, and so that's where I posted it. Okay, now in the chat. Very good. Okay, so Charlie asked about issues with serial correlation. It's actually not important here, in the sense that we're going to cluster our standard errors. Okay, so when I talked about the efficiency issue, yes, you're exactly implicit in that was no serial correlation. But that's only for efficiency. For inference, there's no problem. So if n is reasonably large, we just cluster our standard errors at the the cross-sectional identifier. So if you call that CID, or let's call it, if you cluster at the cross-sectional identifier level, then that accounts for any kind of serial correlation, and it doesn't cause any bias, and it accounts for heteroscedasticity. Okay, I probably should have, to be fair, I guess I should have started at the top of this to make sure. Let's see if I can actually get my.
I think you're set. Except there's one new one now from Brandy.
Oh, okay, good. I will. To tell you the truth, when I saw, oh yeah, Imbens is an ASA fellow too. Sophia, you mentioned that.
Gosh, yeah.
How much more envious could I be? No, I'm kidding. He's a friend of mine, and he deserves everything like that. Actually, I will admit that I kind of wanted to skip over Brandy's question, because the odds ratio has never quite spoken to me, but I've been educated recently, and I know that even for things like studying efficacy of things like vaccines, that the odds ratio plays an important role. So Brandy, here's the short answer. Actually, the coefficients that you get in the, yeah, this is a great question. The coefficients you get if you do a logistic regression are going to be the odds ratio, the average treatment effect on the odds ratio. If you instead use the so-called margins command in Stata, then what's going to happen is you're actually going to get the average treatment effect on the probability itself, not on the odds ratio, which of course is this nonlinear function of the which is this other function of the probability. So yes, you will directly get the odds ratio, and that I'm going to make a note of that to point that out in my paper that I'm supposed to be presenting at the Royal Economic Association in less than 2 months now. So I will mention that for sure. Okay, great. Thanks for those questions. That's good. Okay,
right.
so I think
Chris, go ahead.
I was gonna wrap things up here. I think those are some great questions, but it was a great presentation, Jeff. I really appreciate you making the time to talk to us. I put out your Twitter handle, so hopefully people will find
oh good okay
that link
if they want to, for sure.
If they want to. Those that want to find it will find it.
Right.
And that's great.
Okay.
But thank you everyone for joining. We'll be doing this again in 4 weeks. Frank Harrell will be here. Look for an invitation in the same place you found the invitation to this one. So I hope to see you all again. And thanks for joining, and thanks all.
Yeah, thanks everyone for attending.
Thank you.